Here we go into inference. Today we're going to do Module 19's guide, which is an introduction to statistical inference. We're going to talk about confidence intervals and estimating values that we might not know, which is pretty helpful in the real world. All right, this is the SDSP information that we use from Module 18. And remember that that stands for the sampling distribution of sample proportions. And it is every sample of a certain size from a particular population. For instance, if I had a population of size 5, I could then take 10 different possible combinations of size 2, which we did in the Module 18 activity, where we had AB, AC, AD, AE, BC, BD, BE, CD, CE, and DE. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total different combinations. And those averages or those proportions from the samples become the sampling distribution. Now this is the formulas, or this information is super important for calculating information regarding the sampling distribution. Remember to check if the sampling distribution is normal, our sample size times the proportion of successes has to be greater than or equal to 10, and the sample size times the failures has to be greater than or equal to 10 as well. And then the mean of the sampling distribution is equal to what the population proportion is, which is great. It's an unbiased estimator. The standard deviation is found by taking the square root of successes times failures divided by n. And you'll see different notations. Some people use NQ and some people use N1 minus P. This just means that Q, failures, is equal to 1 minus successes. All right, using the following to fill in the blanks, we want to know what's the value under the center. Well, we know that the center is going to be equal to the population proportion or the sampling distribution mean. Both go in that middle portion here. They're the same thing. The mean here, I would call, you might be able to get away with that, but I would call this for the means distributions, which we'll talk about later, not proportions. The distance from one center out to A, 95%, you know that's 2 standard deviations. We're going to call that 2 times the standard error. And the same thing is going to be true for B, 2 times the standard error. To the next page, we're going to be estimating our sample proportion. Notice that in our Module 18 worksheet that none of the samples had the proportion of blue eyes of being 0.2. The samples were either an average of 0 or 0.5. But when we put it all together, we got 0.2 as the average. So we're going to use an interval to estimate. And we're going to say that this value down here that caps things is the lower endpoint. And the value up here is the upper endpoint. And remember that that is 2 times the standard error, that distance right here. Okay. Now, I want to know what percent of samples has a proportion of success between A and B. Well, what percent of samples? We're going to say 95% we're going to capture. I can move this curve to the left. How far while still capturing the proportion here? With my 95%, I can take this and move it to the right, to the left. This portion, which splits our 95% in half, we're going to be able to move it 2 standard errors to the left. And the same thing for to the right. Because once I move it to the right past that 2 standard error, my confidence interval ends. Now, which percent of samples will produce a confident interval estimate that will actually contain P? We'll say 95%. And this is an estimate, this is not a guarantee. I can't say with certainty that if I had 100 samples that 95 were guaranteed to have P in it. We're just saying 95% of the time approximately that's what we would estimate. Okay. Now, a confidence interval needs a couple of pieces of information to be able to really be valid and tell you something. You need to either have the endpoints of the interval given directly or as a single value with a margin of error. And you see this during times of election where you say that the candidate has, a 63% with a margin of error of 2% popularity. It could be 61 or it could be 65. It's somewhere in between those two. That's what the margin of error is. If you listen and you read this right here, this example says, okay, the poll found that 42% of Americans between this age say they rarely don't get a good night's sleep. More than half say that they experience a sleep problem every night or almost every night. Well, okay, more than half, we're saying 60%, but I don't know what the endpoints of the interval are, and I don't know what the margin of error is. I don't know more than half, give or take what percent higher or below. Well, moving down to the next paragraph says, in the methodology and definition section, we find more detailed information about the poll. The annual poll was conducted. They used a random sample of 1,508 adults between the ages of 13 and 64. The margin of error was 2.5% at 95% confidence interval. So what they're saying is I can have this lower and upper limit where I'm going to be taking my proportion minus 2 times my standard error, and then I'm going to do my proportion plus 2 times my standard error to get my confidence interval. We have 60% minus 2.5% and 60% plus 2.5%. And that's going to be my confidence interval, which gives us 57.5% to 62.5%. And that's with 95% confidence. But what if we don't have the margin of error? Now, the National Vital Statistics Report says the preterm birth rate for 2010 was about 12%. That is saying that P is 12%. That's the proportion of the population. Suppose this year a random sample of 500 births has 52 that are preterm. That means that our sample proportion is 52 out of 500. Using the estimate for the NVS report for 2011 and the results from this year's sample, estimate the percent of preterm with 95% confidence. Okay, well, 95% confidence, we know that we need to take 2 times the standard error, or the standard deviation, depending on if you use population information or proportion information. The formula, which was given above, the standard deviation and the sampling distribution, was equal to the proportion of successes times 1 minus the proportion of successes over n. Oftentimes we don't know the population value. We're actually typically trying to estimate it. And so you'll see this as p hat times 1 minus p hat if we don't know p. But right now we do know p, so we're going to say the sample distribution, standard deviation, is going to be equal to the square root of 0.12 times 1 minus 0.12 over 500. I'm using this information and this information. Now, I have a standard deviation of 0.0145. Now I need to check that the normal model is appropriate. That means I need to check NP greater than or equal to 10 and N1 minus P greater than or equal to 10. That's 500 times 0.12 and 500 times 1 minus 0.12, which gives me 60 and 440 respectively. The normal conditions are met. I then take my sample proportion plus or minus 2 times the standard error, or my proportion of the sample plus or minus the margin of error. So that is 0.104 plus or minus 2 times 0.0145. 0.104 minus 2 times gives me 0.075. Adding it gives me 0.133. I first do 0.104 minus 2 times, and then I do plus 2 times. That's how I get the upper and lower. So now we're going to use an applet to calculate some things.